Hello everyone. In this video, we're going to begin our discussion of a really important and really powerful topic in C++ and really in any programming language, arrays. Let's head over to the notes and see what our learning objectives are for our introduction to arrays. We're first going to look at a few examples and see what an array is and why they're so useful. Then we'll declare and initialize arrays, apply array indexing to get individual items out of and into an array, and then determine the size of an array, which is not as straightforward as you think it would be. All right, so our warm-up task is pretty short. We're just going to code up an empty main function in a file called arrayfun.cpp so that we can write some code related to these learning objectives here. Now, we could write this code to utilize the 3-file format since we know about it now, but for the sake of time and simplicity, most of the code that I will do in these videos will not use the 3-file format, but you're encouraged to either write everything in one file and then at the end break it up into the 3-file format, or just start with the 3-file format. But initially in arrayfun.cpp, we're not going to write any additional functions beyond main, because we won't cover that until a later video, which would be how to use functions, passing them in, how to use arrays and pass them into functions. All right, so let's first begin our motivation for arrays. Remember that a string is a sequence of characters. In fact, each character is at a position, which is synonymous with index or location. So if you read or hear me say index, position, or location, those all mean the same things. In C++, indexing for strings and arrays start at 0 and goes up to n-1, where n is the number of characters in the string. So, for example, I've taken this image from Zybooks, which was in a very early chapter, so I know that you've seen it before. Let's say we have a code that declares a string that stores the sequence of characters M-A-R-Y, Mary. So here's a diagram showing what Mary looks like. The M is at the first position, which is index 0 in 0-base indexing. A is at index 1, the second position. R is at index 2, the third position. Y is at index 3, the fourth position. There are 4 letters in total in Mary, which is what n is. Since n is 4, the valid indices of this string are 0 through 4 minus 1, which is 3. And we see that here on the right, 0, 1, 2, 3. Working with 0-base indexing will be a little challenging. It's a different way of training your brain to start counting, to count at 0 instead of 1. But with a lot of practice, you will get used to it. Now, we can get a character in the string at any index position using the at string member function. So for example, if we want to print out the letter A is at index position 1, we would use name.at1 to get the letter A. And we can find out how many characters there are in the string, which would be n, using the string member function size, such as name.size. We could also use name.length. Either one of these would return 4 in this case. So this is review of what you've already read in a previous section of Zybooks on strings. You may have used some of these member functions like at or size in some of your code before as well. The reason why I'm bringing up these details of strings is to provide some kind of context for learning about arrays. Excuse me. Strings are a sequence of characters. Arrays are a sequence of items where those items can be any data type. They could be characters, they could be strings, they could be integers, they could be doubles. They're really a more general form of strings. So here are some examples of what we could have arrays of. We could have sequences of primitives, like these data types, or of objects, like these data types. This last one I want to comment on a little bit. You can have arrays of your own data types, where you've declared objects of a type that you've defined. This will be covered in the next class after this one. It's a really important concept called object-oriented programming. So be sure to stay tuned and learn about objects, defining your own data types in 122. Okay, so now we have a definition for an array. It's a sequence of items where those items can be really anything in C++. What are some reasons why we might use arrays in our program? Well, I've got a few examples here. There are sequences of items everywhere in your everyday life. For example, here I have an image of mailboxes. So there's a sequence of mailboxes, and each mailbox has a position, just like each character in a string has a position. I have another example here that's kind of fun. Suppose you have a collection, could be a collection of anything. Here's rocks, but it could be stamps or cards or video games, something like that. And you want to display them in an organized manner. So you might put them to be kind of in a line where each rock is at a specific position. Here they're called spots. So each spot is used so that you can find it later. Like you might record that a certain rock is at spot 0 and a certain different rock is at spot 2. And if you ever need to find one of your rocks, you could just look up and see what spot it is. Now in this example, there's only 5 rocks, but imagine if instead of rocks, these were books. And it wasn't a personal collection, it was an entire library of books. So we know we have something called the Dewey Decimal System that we use in order to find the location or spot of a book in a library. And then the last example is more close to home in this class. We've written code such as transactionFun.cpp and advancedfileIOFun.cpp, where we've been working with sequences of values. We've been using those sequence of values in order to accumulate a total so that we could compute an average, such as what we did in transaction fun. Now, each iteration of our loop, we would read in a new transaction value either from the user or from a file, and we would overwrite the previous transaction value with the newly read in transaction value. So at the end of our loop, we would have accumulated all of our transaction values in a variable like total transaction, but we will have lost all of the individual values themselves, right? We weren't storing those somewhere. We were reading in one, adding it to the total, next iteration of the loop, we were reading in one, overwriting the other one, adding it to the total, so on and so forth. So if we wanted to perhaps use that sequence of values later, maybe we wanted to compare January transaction values to February transaction values, we wouldn't be able to do that because we're not holding on to January transaction values, we're just keeping the total. And then when we read in another file or get another value from the user representing February transactions, we're just maintaining the total. How can we keep track of all of these transactions perhaps in a list or an array, such that we could compare them, maybe see at the beginning of the month, do we spend more or less than at the end of the month, for example. Those kinds of data science-y type questions would require us to hang on to those values so we could use them at a later time. And we will hang on to those values in an array. And an array, like I said, is like a string in that you have a sequence of characters, but these can be sequences of items, like sequences of doubles, where each value is a transaction value. We could save those transactions in an array. All right, hopefully you are feeling quite motivated about why we would use arrays in our code. And let's begin our discussion of arrays specifically in C++. So an array is a sequence of items. We already know that. But in C++, they are contiguously allocated. That means that if I had code like this, X might be allocated somewhere in memory over here, and Y might be allocated memory somewhere over here. These are not contiguous. They're not next to each other. But an array, for example, is contiguous. The values are stored right next to each other. For example, here are 4 memory locations storing 110, 7, and 3 respectively that are right next to each other. They're contiguous. This is important because an array only refers to the first value. The rest of the values are referred to as an offset from this first value. That's what saves you having to have, say, 4 different variables, one for each of your array values. Now we can just have one variable that refers to the first one, and we can use indices, positions, or offsets in order to get the rest of the values. It's actually really slick. If your array stored 10,000 integers, you would not want to have to maintain 10,000 variables. You want to maintain one variable and then just specify offsets or indices from that one variable in order to get the rest of the values. It's really useful. Arrays in C++ require that all of the items in the array are of the same data type and of the same size. Comes back to the offset computation that I was mentioning earlier. All items are accessed by the same name but a different index. And another term for index that you may encounter is subscript. And this will make more sense when we learn about accessing elements in an array. We'll use something called a subscript or subscript notation. Okay, an array is a data structure, which is a very, very, very important concept in computer science. In fact, you will take entire classes devoted to data structures. A data structure is a way of storing and organizing data in memory so that it may be accessed and manipulated efficiently. 122 and 223 will cover data structures in detail. But an array is one of our first encounters working with a data structure, or data is structured in a linear fashion for an array. And you can see this linear fashion here in my example that I drew. All right, arrays are used to store related information. You can take a look at some of these examples, but just thinking back to our transaction fund where we have credit card transactions that are all related because they're from the same user. So the diagram that I drew on the board earlier here is linear, it's unidimensional. We can have arrays that are multidimensional. Two-dimensional arrays, which you can think of like an Excel spreadsheet where you have rows and columns. Three-dimensional arrays, which you can think of like a cube, and then 4 and 5, really so on and so forth. In a later video, we are going to work with multi-dimensional arrays. But for now, we're going to stick with the basics, and we'll start with one-dimensional arrays. All right, how to declare arrays. Well, we have to specify what the data type of the values the array is going to store is, such as in this example, int. And then we have the name of our array, just like we would before. But after the name of our array, we have hard brackets with a number inside. The hard brackets denote arrays. Whenever you see these hard brackets, think array. The number inside declares the size. How many integers does this array hold? So for example, here we're declaring an array of 6 integers, and the array is called A. And since we didn't assign any values to this array, those are garbage values. Just like if we were to initialize a variable, declare a variable and not initialize it, there's garbage values at that location. Okay, so here's a nice diagram that shows what this array looks like in memory. So there are 6 cells, 1, 2, 3, 4, 5, 6, and each cell can be denoted by its index, just like with strings. So here's a sub 0, sub 1, sub 2, sub 3, sub 4, sub 5. Note that I'm saying the word sub. That's usually how you read these hard brackets, which are called subscript or subscript notation. So when we declare an array, we can also specify a sequence of values to initialize the array to. In this case, we'll use an assignment operator and curly braces. And in the curly braces, we'll just have a comma-separated list of values. Now, we can, if we want, still specify a size here. It needs to be at least as big as the number of items that we have in our comma-separated list of values on the right-hand side of the assignment operator. But the compiler can also just count and figure out how big is this array. All right, so let's head over to Array Fun and get our feet wet working with declaring arrays. So let's do an array of integers. We'll just call it numbers, and we'll declare it to be 10. So 10 uninitialized integers in the array called numbers, just to describe what this line of code does. Then let's say, an array of strings called words, and we'll omit a size because we're going to initialize it at the same time we declare it. So let's put in here some words. So this here will be 3 initialized strings in the array called words. And always good practice to include the string library when working with strings. Okay, let's make a copy of our words array, and let's call it words 2. This time I do want to put a value in the hard bracket, so this is called the size declaration or the size descriptor, and let's put in 20. So here we have 20 total strings in an array called words 2. 3 are initialized. The rest are empty strings. The reason why the rest are empty strings is we have something called a partially initialized or a partially filled array. And when we partially initialize an array, the compiler will go ahead and zero out the rest of the array for us. There's not going to be any output to this program at this point, but we can still make sure that it compiles and we are properly able to declare our arrays. So here are some additional examples of declaring arrays. You can declare them alongside of simple non-array-like variables. For example, on this first line here, we have the declaration of 3 variables. They're all of type int, except the student's variable is an array of 100 ints, and the teacher's variable is an array of 50 ints. All right, now let's get to some more exciting parts of working with arrays. For example, how can we see what an item is at a particular index in an array? We know with strings we were using .at, right here, in order to specify an index and get a character? Well, we can't use the .at with arrays, but we will use our subscript notation or our array indexing notation, which is the hard brackets. We'll put the hard brackets to the right of the name of a variable that's an array like A. And inside of the hard brackets, we will put a value. This value will be the index. And I can't emphasize enough that indices for arrays, just like strings, are zero-based, which means if there are n items in the array, then we'll use 0 to n minus 1 in order to denote what the valid indices of the array are. All right, so let's head over to our code. Let's print out words sub 0 and see what that is. So here's words. It's been declared to be the array hello, hi, and bye. So we print out word sub 0, which is the first string in the array, and it prints out hello. Let's try another one. Let's say we print out words 2 sub 5. Now, we only initialized the first 3 indices of our words 2 array. That would be hello at 1, hi at 2, hello at 0, hi at 1, and bye at 2. We didn't initialize the rest of them. So what do you think that words 2 sub 5 will print? So it actually prints the empty string because at word sub 5, that string has been initialized to the empty string. All right, so here's a little task for you to try. Go ahead and print out the bye of words 2. So we'll have words 2 sub 2, which will give us the bye that's in the third position of words 2. Awesome. Now, we can also use array subscripting in order to assign a value to an array. So arrays are mutable, which means they can be changed. So let's write that down because it's important. The opposite of mutable would be immutable, which means cannot be changed. So arrays are mutable, they can be changed. If we initialize, say, the first item in our words array to hello, we can change that later if we want. These are not constant and they're not read-only. So let's change hello of words to be all caps, hello. So we'll have word sub 0 is assigned hello in all caps. We just use the subscript notation in order to identify the location of the string we want to change, and then the assignment operator to assign a new string to that location. Okay, looks like it compiles, but we don't have any output. So let's go ahead and see out word sub 0 right after our change so we can see if the change persisted. And it looks like it does. Awesome. All right, let's do a little bit more with indexing into arrays and assignment. Let's say we have another variable. Let's declare an integer and let's call it x. Maybe we'll initialize x to 0. We could use x in order to index into our array. We could say words sub x and print that out, and we'll get hello again. We could also use x in order to assign a value. Let's say we assign word sub x plus 1. Let's say hi in all caps. And then we'll print out words sub x plus 1. Because the arithmetic operator, addition, has higher precedence than the subscripting operator, hard brackets, then this will be performed first, x plus 1 to get the index, then the assignment at that index x plus 1. And we can see we were successfully able to change lowercase hi to uppercase hi. We could do some other crazy things here. Like, for example, let's say we want to print out words sub 1 again, but maybe we want to actually change x to be 1. We could do plus plus x, and that will add 1 to x, and then use x. Remember, this is the pre-increment operator. We could also do something like words, let's do x, let's do post increment, just for fun, plus assign, or excuse me, let's work with numbers this time, so we're using integers. Let's say numbers sub x gets 5, then we'll see out numbers sub x. And then let's do something kind of crazy, like let's do numbers sub x plus 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 assign 100. And then let's print out numbers sub x minus 1, which would be the value that we added 100 to. And then we'll print out numbers sub x just so we can see that value that is currently at x. So I'm just kind of making up some fun stuff here just to show you that you can do some advanced things with determining your array index position and with assignment to arrays. And it would help to spell numbers correctly. Okay, so we assign 5 to x, where x was originally 0. Then we added 1 to x here. So number sub 1 is 5, and then we print out number sub 1, and we see 5. Then we add 100 to the value currently at number sub 1 to get 105, and then we increment x, so x is now 2. Then we print out x minus 1, which is 2 minus 1 is 1. So we print out x sub 1 again, and we see it is 100 plus 5. And then we print out number sub x, and recall that x is 2. Number sub 2 is some crazy garbage value because when we initialize numbers, when we declared numbers, we did not initialize it. So numbers initially was 10 uninitialized integers. Now we have 9 uninitialized integers, but number sub 1 is 105. If we head back over to the notes, we'll see that I have some additional examples in here that you can work through in order to practice using the assignment operator to change arrays. So take a look at these examples here and these examples here. Now I think it's time for you to try writing some code as part of a task. So I have a task for you here. Write a segment of code that creates an array of 10 double values, initializing the array with the values 1.0 through 10.0. Then write code using the assignment operator that exchanges the first and the last values. Go ahead and pause this video and work on this task. You know everything you need to know in order to solve this problem. All right, so we're going to declare another array. Let's call it my doubles. And my doubles is going to contain 10 double values, 1.0 through 10.0. All right, so we're done with the first part. We've declared the array. Now let's scroll down to the bottom of our code. Let's print out my double sub 0, my double sub 9, then do the swap, and then print out my double sub 0 and my double sub 9 as well. So how are we going to do this swap? Well, we want to set the value at my double sub 0 to be the value at my double sub 9. But when we do that, we're going to overwrite the value at my double sub 0 and lose it. Then we won't be able to assign that original my double sub 0 value to my double sub 9. So we're going to need to declare another variable of type double, and I would just call it temp, short for temporary. It's just a temporary variable that we're going to use in order to do this assignment process or the swapping process. So let's assign to temp my doubles sub 0, and then we can now safely overwrite my doubles sub 0 with my doubles sub 9 because we've cached or saved that my double sub 0 value in temp. Then we can assign temp to be the last position in the array, and recall it was formerly the first position in the array. So before the swap, the first item was 1, the last item was 10, and then after the swap, the first item is 10, and the last item is 1. All right, you are doing so awesome. We've learned a lot in this video. We're almost done. Let's go ahead and take a look at this last piece of information in our introduction to arrays. Array length. Arrays are fixed in size. You cannot later, after you've declared an array, say, oh, I want it to be 10 items bigger or 10 items smaller. Once you've declared it, that size is fixed. Now, typically what we'll do is just declare our arrays to be bigger than we need. That way we don't run into this problem later. Soon we're going to learn about vectors, and they're a more advanced version of an array that can grow or shrink in size. But until then, we're going to stick with this. Just declare our arrays to be larger than we need so we don't have to deal with this problem of needing to grow or shrink our array in size. If we're only using a small portion or a smaller portion than the size of our array, number of items, then we're going to want to keep track of how many items in our array we're using. Like, are we using the first 10 of a 20 element array? Are we using the first 1,000 in a 2,000 element array, etc. So in order to do this, we're going to have a variable, typically called something like size, that we'll use to keep track of the number of items in the array. For example, let's head back over to the code. For my doubles, we might have an integer called my doubles size, and we could call it, we could initialize it to 10. If we're always going to use the 10 integers in my doubles, we might make this a constant so that it can't change. As another example, let's take a look at words to. So we might have an integer called words to size. Do we initialize this to 3 or to 20? This is kind of tricky. We might initialize this to 3 and leave it as a non-constant integer because we might add more or remove a few strings from words too. But we might also have a constant integer called words to total size, and this we might initialize to 20, representing what is the max size of this array. We could at most put 20 strings in here. So you'll typically want to declare these integer variables in order to keep track of the number of items and the size, which is the max number of items, in a partially filled array. If perhaps at any point in time you don't have access to the constant integer that represents the total number of elements that can be stored in an array, you can figure that out by doing a little bit of arithmetic. There's a sizeof operator. It looks like a function, but it's actually an operator called sizeof, which tells you the total number of bytes allocated for a variable. So for example, let's say we print out the value of size of my double's size. Recall that my double's size here is an integer. And it prints out 4. In fact, typically, integers are 4 bytes large. We learned about this at the very beginning of the semester when we were talking about different data types. So chars are typically 1 byte in size, shorts 2 bytes, integers and floats 4 bytes, and doubles 8 bytes. Now, using this knowledge of a size of an integer or a size of a double, we could get the size of an array, divide it by the size of that data type, and it should tell us how many of those variables are in the array, or how many of those memory cells are in the array. So let's try this. Let's print out the size of a double value, just to confirm that it is in fact 8. And let's print out the size of my doubles, which is an array. Okay, so we see that the size of a double is 8, and we see the size of my doubles is 80, which makes sense because we declared my doubles to hold 10 doubles. 8 times 10 is 80. So if we see out the size of my doubles divided by size of double, this will tell us that there are in fact 10 doubles in the array my doubles. And there it is. So there's a way you can figure out the size or the maximum number of elements that an array can store. However, my advice is still keep track of this number in a variable, specifically a constant integer if you're keeping track of the total number of elements in the array, and a non-constant integer if you're partially filling that array and you want to keep track of how many elements are you currently using in that larger element array. All right, so this wraps up our introduction to arrays. We learned a lot in this video, but there's still a lot more to learn related to arrays, so stay tuned.